Okay, this one here, we could write in two different ways, but if we left it like that, then the reaction transferred 291 kilojoules. Is the energy absorbed or is the energy released in this particular reaction? Released. So 291 kilojoules of energy released. So we typically try to keep track of the direction if it's absorbed or released. And then we see that what mass of quicklime? Well, quicklime is was processed. Quicklime is this or this? It's this calcium oxide. And so we'll see that there's 1 mole of calcium oxide, quicklime, produced for every 65.3 kilojoules of energy released. And then we just need the molar mass. It's 4008 for calcium, and oxygen is 1600. So that's 5608. So 56.08 grams of calcium oxide per mole. And so what did you get?
249
249. 0.9. Okay. And so 200. And so this will drown to 250 grams of calcium oxide. Yeah. For sig figs, you either put a decimal here, and that means any zero after non-zero with a decimal point is significant. Or we would, do 2.5 times 10 squared grams. This is the way the book's going to do it here, the way you did it. Now, oops, 360. Now, that's not the most common way this reaction is written. The most common way this reaction is written is like this. It's going to be calcium oxide, solid, plus H2O liquid. So we're going to produce calcium hydroxide, solid, plus, okay, not plus. Instead, they'll use this. What does this symbol mean again? This is called the... What do you name that symbol there? That's what it is, but what is it called? Did I mention this yesterday or not at all? This is called the heat of reaction, or the enthalpy of reaction. Heat of reaction. And typically the heat of the reaction, we can tell, for example, if delta H is greater than 0, we call it endothermic. If delta H is less than 0, we'll call it exothermic. And so we can tell here. This is exothermic. This is going to be delta H is equal to minus 65.3 kilojoules. Now the minus sign doesn't have actual meaning. The minus sign just tells us the direction. And so for example, let's say your bank balance dropped by $20, right? And so you might notice negative $20 in your bank statement. Negative $20, does that mean you got a negative $20 bill? No, so energy is like money. There's no such thing as negative energy. No such thing. Just like there's no such thing as a negative $20 bill. The negative is just to indicate the direction of exchange. And so you're losing it out of your bank account, it's negative. If you're gaining it in your bank account, it's positive. And so what that means is, what do we do with this negative sign? For example, if we left the negative sign here, we'd get negative 250 grams. Is negative 250 grams? Is negative 250 grams something you can weigh out on the balance? Somebody says, I'm on a diet. I want negative 250 grams of glucose. Would that work? No, and so there's no such thing as negative. And so what do we do with the sign then? The sign is the direction. And so in this case, we need to assign a sign to the 291 kilojoules. Therefore, this 291 kilojoules was released. And what we do here is we make it minus 291 kilojoules. That was the amount of energy that was lost by this. And now we can use this because it would be for every mole of CaO, we have minus 65.3 kilojoules. And so if we want to keep track of the sign, then we have to assign a sign to the 291, and the sign depends. You know? It's like a $20 bill. If the $20 bill was transferred between your bank account and something else, then which direction? Did you deposit it or did you withdraw it, right? Well, the same thing. If it's a withdrawal, we'll assign it a negative sign. If it's a deposit, we'll assign it a positive sign, and this will keep track of the sign. That way, we aren't going to end up with negative 250 grams, which is totally meaningless. This will be 56.08 grams. And so these are two ways of doing it. And both ways you have to know in order to do it, because you have to be familiar with the verbal. This is why I wrote released here. I wrote released here because we're ignoring the sign. Or we do it mathematical, like this. When we do more complex equations, we aren't going to do more complex equations in Chem 4, but if you do more complex equations in Chem 1A, then you're going to have to keep track of the sign. Otherwise, things aren't going to add up correctly. Okay. All right, so then that's your basic. This is your basic energy stoichiometry problem, and then I added two extra twists. I added the physics on the other problem just to show, the joule definition, and then I added the percent efficiency percentages. But you've already dealt with percentages many times before, so it's just another percentage you got to deal with. And so now we're going to leave chapter 10, and then you need to get back on track here. And we're going to go to chapter 11. So let's take a look. Chapter 11. Chapter 10, I didn't use the PowerPoints because I was thinking I'll save time, but maybe I didn't save any time at all. But let's see about chapter 11. Chapter 11, we're going to revisit the atoms. So chapter 10 is very important in chemistry because we're very interested in the mounts. We've got to calculate the mounts. Chapter 11, we're going to go back and think about, chemical properties and all that type of stuff. Chemical properties, we need to know the composition and, in order to get the properties, we need to know the composition and the structure, right? You know the composition of an atom. The composition of an atom, it's made up of protons, neutrons, and electrons. Well, you know a little bit about the structure. Tell me about the structure that you know about the atom.
Electrons surrounding the
Nucleus, yeah, we have.
And then the proton and neutron. Electrons are.
Yeah. So, well, when you look at the structure, does that really tell you the difference between a carbon atom and a nitrogen atom? No. And so we don't know enough about the structure. And so what we need to do is we need to revisit the structure of the atom in order to differentiate why is a carbon atom different in terms of property than a nitrogen atom. And in order to understand that deeper, we have to look at the theory of chemistry, atomic theory. In other words, the quantum model of the atom. So here are their learning objectives. I'm going to skip those for now, you can read those. Where did the quantum mechanical model of the atom come from? And so when we're looking at the structure of the atom, a lot of insight was gotten into the structure of the atom by electromagnetic radiation. Electromagnetic radiation is just a fancy word for light. So there are lots of different types of light. We have regular visible light from light bulbs. That's here. We have ultraviolet light from some light bulbs emit ultraviolet. The sun emits ultraviolet. We have infrared. Most light bulbs emit infrared. Infrared is heat. Ultraviolet and infrared are invisible. Visible is visible. White light. We also have very high energy. You know, ultraviolet is damaging, but what's more damaging are X-rays. And what's more damaging than X-rays is gamma rays. And then we have lower energies than infrared, which would be microwaves and radio waves. And how light and matter interact gave us a lot of insight into the structure. How light and matter interact is called spectroscopy. It's the interaction of light with matter, spectroscopy. And one thing to note about all these, light moves at the speed of light, you know, so it doesn't matter if it's a gamma ray, which is very damaging, versus radio waves, a lot less damaging. Gamma rays, radio waves, they both move at the same speed, that is the speed of light. How fast is the speed of light? It's actually 2.998 times 10 to the 8 meters, which could either round to 3.0 or 3.0 or 3 times 10 to the 8 meters per second, or 186,000 miles per hour. And so light, you know, gamma rays and radio waves, they move at the same speed, but they pack a different punch. You know. And so we're going to look at some characteristics of light here. And what are some of the differences? Even though these are moving at the same speed, one of the properties that are different between those are the waves. We can describe these light beams as waves. We have something called the wavelength and the frequency. And so there's a big difference between the wavelength and the frequency of gamma rays versus radio waves. Gamma rays have very high frequency, radio waves have low frequency. Gamma rays have very short wavelength, radio waves have very long wavelengths. And so based on the wave, and we'll take a look at this next slide, based on the waves of this here. So when we look at gamma rays, these have a lot of punch. Even though they're moving at the same speed as the radio waves, they're going to have much higher frequency. And so imagine this wave moving at you at the speed of light, which is 186,000 miles an hour. Then what you're going to see is this wave, you know, and the wave oscillates from peak to trough. And what is this oscillation? This oscillation turns out to be an electric field and a magnetic field oscillation. In terms of an electric field oscillation, you got to imagine it as being plus, minus, plus, minus. This is what we call electric field. And so as this thing's coming at you, it's oscillating plus, minus, very fast. It's moving at 186,000 miles an hour. Whereas, you know, radio waves like this, they're moving at the same speed, 186,000 miles an hour, but they're going to oscillate at a slower rate, between plus and minus. But they're moving so fast that even though they're oscillating at a slower rate, it's still very, I mean, you'd think it's a very high frequency because like FM radio is megahertz. Or hertz is how we measure the frequency. 1 hertz is 1 cycle per second. And so hertz would be starting at the top, dropping down here, and then going back to the top again, 1 cycle. And so even radio waves, which have low frequency and long wavelength, are still megahertz, 1,000,000 cycles in 1 second. And so it seems, it's just, you know, 1,000,000 cycles in 1 second is huge. But these are moving way faster than 1,000,000 cycles per second. You know, even microwave, you know what a microwave operates at? Microwave operates at gigahertz. At gigahertz. And so mega, then what comes next? Giga? It's a billion cycles in a second. The wavelengths here are often characterized as well. The wavelength is the peak-to-peak distance here. And so when we look at it, X-rays are on the order of atoms, whereas this is the wavelength, peak-to-peak or trout-to-trout, the distance there. The wavelengths are 10 to the minus 10 meters, about the size of an atom. Well, radio waves have kilometer, 1,000 meters, kilometer or bigger, peak-to-peak distances. Even though the peak-to-peak distance is huge, this would be a million meters here. Its frequency is still fairly high. Oh, those are radio waves. There's FM here. Microwaves. Correct. So let's see some animations of light. So we can just see an animation here. One of these is the electric field. The perpendicular to that is the magnetic field. Magnetic field would be oscillating north-south, north-south. Electric field would be oscillating plus, minus, plus, minus. Sorry, the video's not so good. Let's fast forward this to see if we can get some animation here. The audio is not so good right now, but we'll just fast forward this to see. Okay. Try one more here. Okay, here we can see. So this is going to be moving basically at the speed of light, and so we're going to just oscillate the electric curve here. Then we have amplitude, which is the height of the wave, but mainly we're interested in wavelength, which is given the symbol lambda, and the frequency, which is given the symbol mu. Here we can see sound wave. Sound wave is different than light wave. The speed of sound is different than the speed of light. Speed of light is almost instantaneous. Speed of sound is much, much slower. We can see different colors will have different wavelengths and different frequencies. And so here, basically we'll do this. So we'll start off with the highest energy form of light. This is going to be electromagnetic spectrum, I'll abbreviate EEM spectrum. think about the highest energy, we have gamma rays up here. And then lower in energy than gamma rays, the energy. Lower in energy than gamma rays, we'll have X-rays. And then lower in energy than X-rays, we're going to have ultraviolet, UV. And then we're going to have visible light. For visible light, we have to remember this. The highest energy visible light will be violet, which is next to ultraviolet. Ultraviolet is just beyond violet. And then it's going to go this: indigo, blue, green, yellow, orange, red. Okay, so red would be the lowest energy visible light, and violet would be the highest energy visible light here. The easiest way to remember this is, so people remember, do you know how people remember this?
It's the rainbow.
It's the rainbow, yeah. Do you have the colors of rainbow memorized? Yeah. A lot of people memorize this as Roy G. did, starting off with red. And then just on the other side of red is what? IR, which stands for infrared. And then below infrared, we have microwave. And then below microwave, we have radio waves. TV. TV now over cable. Used to be over. And so the difference here is this: the speed. The speed is all the same, right? It's a constant. And that constant is called c, and that c is equal to 3.0 times 10 to the 8 meters per second, or 186,000 miles per hour. But when we look at the wavelength, wavelength is given the symbol lambda. And then when we see this is going to have very short wavelength, whereas down here, these are going to have long wavelength. And so the longer the wavelength, the lower the energy. The shorter the wavelength, the higher the energy. And so what this does is this. You know, chemistry is, what's the most important force in chemistry? Gravity, is it? You see? Gravity, electrical forces. Electrical forces are going to be the most important. So let's imagine this is oscillating between plus and minus. So if it's oscillating between plus and minus like this, in the atom, the nuclei are kind of massive, you know, they have a lot of inertia. But what about the electrons? Are the electrons massive? Do they have a lot of inertia? The electrons are very light, right? They don't weigh that much. Like 1/2000th of a proton's mass or neutron's mass. And so imagine if you're an electron. You're an electron, it's like this. Imagine you're a massive ship in the ocean. If you're a massive ship in the ocean, are you going to be impacted by little waves? No. But what if you're a little buoy, or what if you're on a little dinghy? Are you going to be impacted by the waves? Yeah. And so if you're an electron in an atom, what's going to happen is, you're going to be hit by these waves. And if this wave is oscillating like this very rapidly, then what's going to happen? You're going to start oscillating very rapidly. So you're a tiny boat in an ocean of waves. Whereas down here, the radio waves, you're going to be oscillating a lot slower. And so this is how we envision what's happening here. With microwaves, these microwaves, let's go with radio waves. With radio waves, these excite electrons in metals. And so in the older cars used to have antenna that would come up. Have you ever seen an older car with an antenna that looks like a little pole? If you try to, if the antenna breaks off, which often happens, then people would use a metal clothes hanger to attach it. Have you ever seen that?
Not the metal
different era. But yeah, people would use a metal clothes hanger because they didn't want to buy the replacement antenna, which was pretty expensive. But electrons and metals are easily excitable, you know, because the electrons aren't so tightly held. But what if they use plastic instead of metal? Would plastic make a good antenna? No, because in plastic, the electrons are very tightly held and they're hard to excite. And so we excite electrons in metals. Microwaves, what microwaves can do is these can rotate small molecules. So for example, water. Did you know water has a positive and a negative end? Do you know what end is negative in water? And which end is positive? It turns out the oxygen is negative. We call it delta minus. We'll talk about that later. And the hydrogen end is positive. Called delta plus. And so what happens is if there's plus minus waves, these waves are plus minus, what's going to happen to the molecule? It's going to be flipping back and forth like this, and eventually it's going to start to rotate. And so this will rotate. You know what infrared does? Infrared has a little more energy. And so if we look at the water, if the oxygen is negative and the hydrogen's positive, then what happens with infrared is as the wave is oscillating like this, the bond, what holds this hydrogen and oxygen together is called a bond. The bond starts vibrating like this because of the positive negative nature of the bond. And so infrared causes vibrations.
To anything? Or to like bigger?
Well, it causes vibrations to what we call, we haven't gotten to bonding yet, but it causes vibrations to polar bonds. If we have a non-polar bond, it doesn't cause those to vibrate. And so, for example, the nitrogen and oxygen in this room are not good greenhouse gases. They're not good greenhouse gases because they're non-polar. Whereas the CO2 and the water vapor in this room are good greenhouse gases because those will absorb infrared. Does it make sense? And so infrared causes vibrations. What visible light does is it excites electrons in matter. And so, you know, different substances like this black object absorbs, you know, all the colors of the rainbow because it can excite the electrons to different levels. The colored objects like this blue are going to absorb different colors of light. What gives it color? What absorbs? Well, the electrons are absorbed. UV. UV. What happens with the UV is it causes bonds to break. And so the thing that's holding the atoms together gets so excited it breaks. You know? And so it can't take that much oscillation. It breaks bonds. This is why UV is damaging. However, X-rays cause the electrons to become so excited, the electrons actually get knocked off matter. If the electrons get knocked off matter, or the atoms, we call it ionizing. And so gamma rays and X-rays, this is ionizing radiation. Ionizing means to create an ion. And so if you knock off the electron, you're going to be left with an ion. And so ionizing radiation. And so this knocks electrons off atoms. It knocks electrons. And so the frequency is very important because of how it excites the electrons. Okay, so how matter interacts with light. Matter and light interact. It's called spectroscopy. The measurement of this is called spectroscopy. Measures this. So we'll take a break and then we'll look at the spectroscopy.